Alright, continuing on. When to use a normal CDF to find a probability when the data is given. When to use the inverse normal. So normal CDF or inverse. When the percent or area of a probability is given and we're trying to find the corresponding score. Oh boy. So here, when I'm given the data or the score, if they give me the score, I use normal CDF to figure out certain probability. If they give me the probability, remember the probability is the area, and the area under this bell-shaped curve, if I measure all of this, all of that area adds up to exactly 1, which stands for 100%. That's all of it. And that's what makes normal distribution very nice to play with, or simple to play with. So here we go. The completion time to run a road race are normally distributed. Very good. That means it's a bell-shaped curve with a mean of 190. The mean is 190 minutes and a standard deviation of 21 minutes. Very good. Now, question. What is the probability that a randomly selected runner, some x, will finish the race in less than 150 minutes? Now, you guys, we don't need the figure on the right, but I'm going to use it anyways. The average is 190, and we're trying to figure out a score to the left, 150. So somewhere down here is 150. I'm not sure how that works. Well, I could convert to the z, but why should I? My calculator could do all the work. Why should I do any extra work? I could just go second distribution, go to normal CDF, and all the way to the left. Isn't that all of this area? So this left is negative 1 to the 99. Very good. Got it. And I want 150. The average we agreed was 190 with a standard deviation of 21. Enter and give me that probability, and that's it right there. Got it. That's all we have to do. And that's how we solve probabilities and really very complex problems by simply using the technology. What's the catch? You need to know which distribution to use and how to use the technology. And what does your answer mean? This is 2.841% chance of that happening. Now, the beauty of it, if we're dealing with the same problem, the calculator already stored. It didn't lose the values, so it already have the average and the standard deviation in there, right? So it says, what percent of runners will finish the race between 205 and 245 minutes? Well, this is 190. 245 is to the right. 205 is to the right. And 245 is also to the right. I could convert this to a z-score. Back in the days, we had no choice because we used the z-table. Now with the technology, guess what? The calculator could do it. Just tell it what to do. Go to normal CDF. What's the lower end? 205. What's the upper end? 245. The average is already stored, like I said. What standard deviation is there? Paste and tell me what that area, and there's my answer. So, this is as complex as things are gonna get. We need to figure out which formula to use and how to input it in a calculator. Once you get that out of the way, then the rest should really come out to be much simpler. So that is 23.3% chance. Now, the book might run to the nearest percentage. That's not a problem. How about this problem? A construction zone on a highway has a posted speed limit of 40 miles per hour. So that's the posted speed limit. The speeds of vehicles passing through this construction zone are normally distributed. It fits under a bell shape with a mean. So the mean of these cars driving is 46 miles per hour with a standard deviation of 4 miles per hour. Very good. What percent of vehicles exceed the speed limit? So let vehicles drive. What percent of these vehicles exceed, what's the speed limit? The speed limit is 40 miles per hour. Again, I don't need to convert to Z. I could just plug things in, but I know the average is 46, and I'm looking, 40 is to the left of, that's the only thing I need to know, and I'm looking for that area. That's the only thing I'm going to use that for. So if I take second distribution, let's go to normal CDF because it's normally distributed, and what we're going to put in, 40 is the lower end, the upper end is 1, so that's 1 times 10 to the 99. What is the mean in there? The mean was 46 with a standard deviation of 4, I believe. Let me just double check. Yeah, it is. Tell me what the answer is, and there it is, 93.92%. So the chances, since the average is 46 and the speed limit is 40, so you would expect a lot of people to be going over the speed limit. So, a cop should figure this out and probably stay there the whole day. That's roughly 93.32% chance of that happening. Okay, what else? If a police, and this is crucial, you guys, if the police wish to ticket only those drivers whose speed falls in the upper 20 percentile, what is the minimum speed limit of a driver that will be ticketed? Let's see. Here, 20 percentile, if you remember, percentile cuts the percentages, separates the top 20% from the bottom 80%. We're trying to find a score. And to find a score, we're going to use inverse. So we're trying to figure out what the score should be. We're going to use our inverse normal distribution. We're going to go for the number 3. What is the area? We want an area of 0.20 if you want the right. Excuse me. What's the average? The average was 46. What's the standard deviation? A 4. Is this a left tail? Nope. Is it a center? No, it's a right tail. And go down. Tell me what the score is. 49.37. X should be 49. .37 miles per hour. Remember, the average was 40. So, those people are driving above 49.37 miles per hour. Those are the people you want to ticket if you only want to get 20% of, if you want to get the 20 percentile of this. Again, that area. And that concludes section 6.2.